Stepping through in our development of understanding of electromagnetic induction, the next topic is about magnetic flux linkage. It's a bit of an unusual term, but the understanding behind it, it's actually quite a straightforward concept once you've got the grasp of it. But to make sense of it, we need to go back again and look at what happens when we're looking at a single coil in terms of the EMF that's being produced. So this is just reproducing the equation that we finished with in the last video. So EMF is equal to delta phi on delta t. Now, if we have a solenoid that has multiple coils, so we're now looking not just at one coil, we're looking at multiple coils, and we'll use the letter capital N there. We're basically, if we've got multiple coils, what we've effectively got is multiple areas that are sort of stacked on top of each other. The total flux then through the area of through the total area is going to be increased by the number of coils. So that means then that our change in flux is going to have increased simply because we've got more coils present. So what we can write there instead is that EMF is now going to be equal to the number of coils multiplied by the rate of change of flux, so N delta phi on delta t. So that that quantity that we'd consider at the top, so if we look at N delta phi, that's the quantity that's known as magnetic flux linkage. And like I said, the term itself is a bit of an unusual one. The easiest way to think of it is just being the total flux across a number of coils. So the total flux acting on all coils in a solenoid. Now, the reason why we bother talking about magnetic flux linkage is that Faraday's law relates specifically to magnetic flux linkage. Faraday's law is, again, it's sort of a step further forward along this idea of understanding about EMF. So Faraday's law states that an EMF in a circuit is equal to the rate of change of flux linkage. So that equation that we just jotted down is basically just stating what Faraday's law is. So EMF being equal to N delta phi and delta t. And if we have a solenoid, then we've got multiple loops. So N being the factor that increases the flux, and hence the flux linkage. Now, if we combine that with Lenz's law, so basically now this takes into account the direction that current would flow. So I'll just make that note. We can take that just one little step further and show that the EMF will now be in a specific orientation, or the positive to negative means that we now need to incorporate this negative here. So that's the only change we need to make to the equation, being equal to N delta phi on delta t. And you will notice that that's in the data booklet, so that's an important equation there, dealing with looking at the flux linkage and how it relates to the EMF that will be produced. So note there that the way that I've written that with the n out the front, sometimes you'll see that written as n delta phi in the numerator, so n delta phi on delta t, so flux linkage over time. Either way, it doesn't really matter which way you make sense of it, but just be aware that the flux linkage is n by delta phi. One last little point here as well, considering that we're dealing with coils, imagine then if we had a solenoid that was moving through a magnetic field, each one of those coils would then contribute to the EMF that's being produced. So we can go back to that equation of EMF being equal to BLV. So if you think about L as, say, being the circumference of the coil, and V as being the speed with which the solenoid is moving through the field, that length would be for one coil, so we could then take that equation one step further as well and add the number of coils to it. And again, the reason why I'm mentioning that here, it's in the data booklet. So if we take the number of coils, or the circumference of one coil, multiply it by the number of coils, we've got that total length effectively, and then we multiply that by the magnetic field strength and the speed with which the solenoid's moving, and you could calculate the EMF that way as well.